So now that we have just kind of a handy reference with all of our rules for differentiation, let's just kind of remind ourselves they're all in play when we take the derivative of a function. Now that we could do 20 examples here, and that's probably how many it would take to really incorporate every single rule. But let's say that for each function, or for each, we'll say for each function, we're going to work two examples. We're going to find dy over dx. So the first example we're going to look at is we're going to look at y equals the sine of x squared over 3x. Now then, there's a couple of things we could do. We could actually take 1/3 out and then take the derivative just of sine of x squared over x, or we can treat 3x as our entire denominator and do the quotient rule right away. I'm going to go ahead and jump into the quotient rule, and then we'll sort of sort out what happens with this 3 later on. So taking the derivative of the left side, that's obviously going to be just simply dy dx. And then I need to apply the quotient rule, which says, if you think again of that low d high minus high d low over low squared, 3x times the derivative with respect to x of the sine of x squared minus the high sine of x squared times the derivative of the low, the derivative of 3x. And this is all over the denominator, 3x quantity squared. And this is where your notation is really important. If you have good notation, it'll tell you what to do. It tells me now I need to take the derivative of sine of x squared. I know the derivative of sine of something is cosine of something times the derivative of that something. So here's the chain rule worked into this. So I have 3x. The derivative of sine of x squared is going to be cosine of x squared. And then I need to make sure I apply the chain rule to take the derivative of x squared. Over here, I've got sine of x squared times the derivative of 3x. Derivative of 3x is 3. So this is minus 3 sine of x squared. And it's all over 3x quantity squared is 9x squared. Okay, my notation tells me I need to take the derivative of x squared here. Well, the derivative of x squared is 2x. If I multiply it by 3x, I get 6x squared cosine of x squared. And it's going to be minus, not equal to, minus 3 sine of x squared. So that's a minus sign right there, all over 9x quantity squared. Now that if I take a look at what I've got in common with each term, I've got x squared here, x squared here. I don't have an x squared in front of the sign argument. I can't cancel what's inside of an argument with an algebraic term right here. But I do have 6, 3, and 9. I can divide out a 3 here. So that gives me just kind of a way of simplifying it. 2x squared cosine of x squared minus the sine of x squared all over 3x squared. And there's that 3 kind of coming into play that we could have addressed earlier, but it was pretty easy to divide out. All right, so that's how we found the derivative of y with respect to x of that particular function. Let's take a look at the equation 2x equals 2y plus 2x squared y cubed. And again, I want to find dy dx. Well, this was an explicit. Y was stated explicitly as a function of x. This is my way of reminding you, hey, we also know how to implicitly find dy dx. So I can take the derivative with respect to x of both sides. Let's kind of remind ourselves that that's a valid move. 2y plus 2x squared y cubed. Okay, so the derivative with respect to x of 2x is simply equal to 2. That part we know. If I take a look at the derivative with respect to x of 2y, well, the derivative of 2y with respect to y is 2. But make sure if you're differentiating a function of y with respect to x that you get this dy dx step right here. Now then, if I take a look, I then need to take the derivative with respect to x of this product. And I could leave 2 in front of x squared, or I can go ahead and factor it out and say this is going to be 2 times the derivative with respect to x of x squared y cubed, like so. And then that way I can very clearly see product rule x squared times y cubed and execute the product rule there. If I keep the 2x squared, it actually still kind of comes out in the wash. So this is a very valid move. I did my sum and difference. I took the derivative with respect to x of 2y. That's here. And now I need to take the derivative with respect to x of 2x squared y cubed, and I went ahead and pulled the 2 out. So now I need to differentiate with respect to x what's inside the parentheses right here, which is that product. So copying everything down, 2 equals 2 dy dx plus 2. All right, if I want to take the derivative of a product, it's the first x squared times the derivative with respect to x of y cubed plus y cubed times the derivative with respect to x of x squared. So there's my product rule laid out. First derivative of the second plus second derivative of the first. So I have 2 equals 2 dy dx plus 2. Okay, I've got x squared, derivative of y cubed with respect to x. Let's go ahead and copy down the x squared. Well, I take the derivative with respect to y, which is 3y squared. And then because I'm differentiating a function of y, I get dy dx. And then over here I get y cubed times the derivative of x squared, which is 2x. All right, I've taken the derivative. Now what I need to do is I need to get dy dx by itself. First thing that I see I can do, and I'll kind of simplify some of these terms along the way, but let's also distribute this too, that we had initially pulled out because we can take a constant multiple out in front. So I get 2 equals 2 dy dx plus, all right, 2 times 3, that's going to be 6x squared y squared dy dx. And then if I distribute the 2 here, I get 4x y cubed. All right, remember when we want to solve for dy dx, I want to get everything with dy dx on one side, anything without it on the other side. So I've got my dy dx's over here. 4xy cubed needs to go over to the other side. So 2 minus 4xy cubed equals, I'm going to go ahead and factor out my dy dx right here. So that's going to be 2 plus 6x squared y squared. And now to get dy dx by itself, I've got dy dx equals 2 minus 4xy cubed over 2 plus 6x squared y squared. And the only thing that I see here that I can do to simplify it, I can take a 2 out of each term. In fact, if you go back to the original equation, I actually could have started by dividing out that 2 and made life easier on myself that way. But I can do it in this step as well and say dy dx is equal to 1 minus 2xy cubed over 1 plus 3x squared y squared. And again, I get a function of x's and y's, but there is the rate of change of y with respect to x for this particular equation right there.